Hello and welcome to this video titled Network Math Hexadecimal. In this video I'm going to teach you everything you ever want to know about hexadecimal. You're going to learn what hexadecimal numbers look like, how they actually incorporate letters as well as numbers, and you're going to learn how to convert from decimal into hexadecimal and back again. So let's learn hexadecimal the same way we learned binary. So once again, starting with base 10, we don't have to recap that again. We know how base 10 works. Now, decimal, base 10, hexadecimal, base 16. So somebody with a very cruel and twisted mind came up with this. So in base 16, we still have our ones position, but guess what? Now instead of multiplying by 10 or multiplying by 2 to get to the next slot, we multiply by 16s. Now let me hold off here before I do that. So in base 10, this spot right here, we had 10 digits we could choose from to put in that single spot. A 0 through a 9. Those were our 10 digits. So that means in base 16, in this spot right here, I have 16 digits I could choose from. What does that look like? Well, the first 10 of them are what you already know. 0 through 9. That covers the first 10. Well, what about the last 6? What do those look like? At this point, we start using letters. So I could actually put into that spot right there the letter A, or B, C, D, E, or F. And each one of those means something. So for example, if I have the letter A right here, that would convert back to decimal as the number 10. If I put a B in there, that would convert back to 11, C is 12, D is 13, E is 14, and F is 15. And that's as high as you can go in one slot. So those are our 16 characters that each placeholder could have, 0 through F. Now, like I said, this is a base 16 counting system. So that means the next value is 16. And then to get the one after that, we take 16 times 16, which is 256. And we can keep going. 256 times 16 is 4,096. And this is one of the real power or benefits of using hexadecimal as a counting system, because we can take a really large number and represent it with just a few digits. So for example, let's start out with something easy here. Let's say I gave you the number 5. And by the way, not always, but a lot of times, for example, if you see the number, let's say 1, 1, well, that could be a decimal, which would be 11. That could be binary. And with only 2 digits, that means the 1 bit and the 2 bit are turned on. So in binary, that would be 3, right? The 1 bit and the 2 bit are turned on. Or this could be a hexadecimal number. So how do you know? Well, I'm not going to worry about binary, but in hexadecimal, a lot of times hexadecimal numbers are preceded by 0x. So if you ever see a value that starts out with 0x and then something, that would mean you're looking at a hexadecimal value. So this right now would be 0x5, what I have right here. Well, if I only have a single digit, whether it be decimal, binary, or hexadecimal, they all mean the ones position. So this is 5 times 1, which is 5. Now what if you saw this? 0xc. Well, right there, even without the 0x, you know that's hexadecimal, because decimal doesn't have any letters in the counting system, and binary doesn't have any letters in the counting system. That's got to be hexadecimal. And now you know that 0 through 9 are normal, so what's C? Well, we know that A is equal to 10, B is equal to 11, C is equal to 12. And because I only have one spot here, that's 12 times my ones position. So that's the number 12 in decimal. So 0xc in hexadecimal is the same as 12 in decimal. What if I put an F right here? 0xf. Well, in my hexadecimal counting system, F was the highest number I could get to. Remember, we had 0 through 9, A, B, C, D, E, and F stood for 15. So if I have an F here, if I say 0xf, oops, sorry for my chicken scratch, let's do that again. 0xf, once again, this is the ones position because I've only got one digit, so that would be 15 times 1, which is the number 15. Now what if I have this? 0x1a. Now I've got two values, right? 2-bit positions. We know the first one is the ones position. The next one is the 16s position. So the way you translate this is 1 times 16. I've got a single 16 plus a, which is 10. So I'll just put that down here in parentheses. A times 1. So that's 10 times 1. So this ends up being 16 plus 10, which is 26. So 0x1a means I have a single value of 16 plus 10 values of 1. So 16 plus 10, 26. What if I gave you this? AB, 0xAB. All right, that means in the 16s position, I have A times 16, and we know that A is 10. So that's 160 plus B times 1, and we know that B is 11. So that ends up being 11. So 160 plus 11, 171. So 0xAB is 171. We have 10 16s, so 16 times 10, plus 11 ones, because A is equal to 10, B is equal to 11. Let's just do one more. What if I had 0x2 1D? Pause the video for a second, see if you can figure that one out. Okay, so in this one, we've got 3 positions. So this right here is 2 times 256, because that's in my 256's position, which is 512, plus 1 times 16, which is just 16, plus, now what was D? A, B, C, D. 10, 11, 12, 13. So D is 13. So we have 13 times 1, which is 13. So what does this give us? 512 plus 16, which is 528, plus 13 is 538, 39, 40, 41, which is 541. So if I did my math correctly, 512 plus 16, 16, 26, 27, 28, that's 528. 28 plus 13, 38, 39, 40, 41. So that's 541. So 0x21D is 541. Let me give you some and see if you can figure them out. How about 0x1E? Pause the video and press play when you think you've got the decimal equivalent of this. Okay, so in this case, we have 1 times 16, which is just 16, plus 14 times 1, because E is equal to 14 in hexadecimal. So 16 plus 14 is 30. So 30 was the answer to that one. Let's do another one. 0x 1 3a. What's that? Pause the video for a moment, figure it out, and then press play. Okay, so in this one, we have 1 times 256, because at third bit position, this is the 256s, plus 3 times 16. So here we have 256 plus 48, plus A is 10. So 10 times 1, which is 10. So 256 plus 48. So 56 plus 48 is what? 56, 66, 76, 86, 96, 106, 104. So that'd be 304. If I did my math correctly there, hopefully. 304 plus 10. So if I'm doing this in my head here, but I believe that is 314. Now, just like with binary, let me now give you a decimal number and see if you can convert that into its hexadecimal equivalent. Let's start easy. How about the number 20? Pause the video and tell me what the hex equivalent is of 20. 0x what? Well, with 20, we have 1 in the 16s position and 4 left over in the 1s position. So 0x14, a single 16 plus 4 1s. Let's do 2 more. How about the number 100 in decimal? What is that in hexadecimal? Pause the video and press play when you think you have the solution. Okay, so let's figure this one out. This is a little bit tougher, so I have to count this on my fingers. I know it's not going to be 3 digits because we're not up into the 256s, so it's going to be only a 2-digit number. So it's going to be some value or multiple or increment of 16. So how many multiples of 16s do I need to have to fit into 100? Well, I've got 16, 32, 48, 64, 80, 96, and that's as close as I can get. So 6 instances of 16 gives me 96 plus 4 left over. So 0x64, if I've done my math correctly, will be 100 in decimal. And just like I did with binary, where would we see these in actual networking commands? Well, here's 3 examples of this. In the world of IP version 6, which if you don't know it, you will need to learn it for networking purposes, IP version 6 addresses are entered as hexadecimal values. Clearly you can see this one's got letters in it. And every time you see letters, you should think, hexadecimal. Cisco routers and switches have something called a configuration register, which dictates how that device will act when it first powers on or boots up. That is represented as a hexadecimal value. Notice that it's preceded with 0x, which means we know that's a hexadecimal value. Switches have something called MAC address tables, where they store MAC addresses of the devices that they've connected to. MAC addresses on switches and on your laptop or PC are represented as hexadecimal values. And so you can see an example of that right there. So thank you for watching. That concludes this video on network math.